right. Good morning, everyone. So, in today's lecture, I am going to show an application of the approximation bound for POMDPs that we derived last time. This is in same spirit of the packet drop example that we did last time, but it will look at the more general model. The motivation comes from what are called certainty equivalent policies in LQG. Okay. So, as I mentioned yesterday, LQG are these models where dynamics are linear and noise is Gaussian and the optimization criteria is quadratic. Now, something very interesting happens in these systems, and there are different results which go under the term of certainty equivalence. So, what happens in a linear system? So, if I have a linear system with deterministic dynamics, the optimal control law is of the form of some scalar multiplied by the state. Okay. So, this is a matrix multiplied by the state with matrix of appropriate dimensions. So, from the state I get an action. Okay. Now, if I look at stochastic systems, so this is deterministic system as in MDP, stochastic system which is MDP. So, the dynamics have additive noise. The optimal control still has the same form. Okay. And when I go to partially observed version of the problem, the optimal control has the form of where this is the MMST estimate of the state. So, this is a super practical result, because that means if I am interested in doing control for a system which can be approximated as a linear system. So, maybe I am doing trajectory control of a rocket, I can run a filter which tries to estimate where the rocket is, and while using control, I can simply assume that my estimate was the true state, and I use the same solution that I have for the stochastic system or for the deterministic system. Okay. It's well known that this structure breaks down if I break any of the assumptions of the model. So, if I go beyond linear systems, or I remove the quadratic cost, or I change the noise from being Gaussian to something else, this structure is no longer optimal. Nonetheless, this is a very useful structure, because I have a separated controller. I first do estimation, and then the control problem is relatively simple, because I am using the optimal control for the fully observed system. So, we are going to ask the following question: can I do something same if my system is not LQG? Okay. So, I will keep this setup, but I will remove the assumption of a linear system. So, I have some general POMDP. I am interested in finding the solution to the POMDP. So, what I would have to do is the following. I need two components, right. So, I am going to remove the linear assumption, and if I remove the linear assumption, it is no longer clear that I have to work with MMSC. Okay. For a nonlinear system, computing MMSC can be complicated. So, I am going to say some estimate of the state. I do not really care how that is created. It can even be just something that I make up, does not have to be consistent estimator or an unbiased estimator or anything like that. I just want, looking at the history of observations, I pick some estimate. Okay. So, to give an example, suppose I compute the belief, suppose my state was real valued, I compute the belief, and the belief happens to be something like this. Okay. I can just say, look, I am going to pick the top point of this, so the mode of my distribution as my estimate. Okay. Or I can say, I am going to look at some confidence interval, and I will randomly pick some point in that confidence interval as my estimate. So, I am going to assume I am given an estimator which looks at the history of observations and gives me a value of the state. And then the procedure that I am going to think about is, I have the model M, which is a POMDP, and I have this history compression function, which is giving me a model M hat with state space S, action space A. And I want to pick some choice of the dynamics and cost here, so that I can use this policy in this model. An obvious choice is, I am going to pretend these are the true dynamics of my system. Okay. So, I am going to think, let me look at this MDP problem, right. So, this guy becomes an MDP. I look at the actual MDP and I compute the optimal policy of the MDP. I am going to call that, since I am calling the MDP M hat, I am going to call the optimal policy pi hat star. Okay. And now, my certainty equivalent control would be, I will sometimes write it by pi CE, but just for ease of writing on the board, I will just say this is pi. This is going to be pi hat star with sigma. Okay. So, at any history, when the certainty equivalent policy has to choose an action corresponding to this, I look at the optimal policy. So, first I do the state estimate, I compute some estimate of the state, and again this is not unbiased, consistent or anything like that, I just pick some estimate and I use the corresponding MDP policy. If my system was an LQG system, this coincides with the standard certainty equivalent model, and in that case I know that this policy is optimal, but I want to say what happens if I use this in a system where it is not optimal anyway. And these types of things are used quite often. For instance, in robotics, you often have do not have the exact observation of the either the location of the robot or the orientation of all the joints and so on, and you would run an estimator to figure out what is the my best estimate of where all the joints or the location of the robot is, and from that point onwards I will use the optimal controller corresponding to full state observation. Okay. So, does the setup make sense? Okay. So, the simple observation is that this is, so it is clear that this is a type of model approximation that we have been talking about, and I would like to argue, so let me define S hat t to be the compression of the history at time t, and I would like to argue that this is an epsilon delta AIS, and my objective is to quantify what epsilon and delta are. Okay. If I can figure out the model distance between my approximate model and the true model, I can use all the results that we had derived earlier in order to get an approximation bound. Okay. So, I am going to start with an assumption on the model which kind of is not too restrictive. So, I am going to assume that my state is a metric space. this is reasonable. Basically, what's happening is I have some distribution. I'm going to take some mean of this distribution, and the results effectively are going to depend on, loosely speaking, how far away is that, assuming that my belief is a delta function from the case when it is some distribution. So having a metric structure on the state is going to make my life easier. In addition to that, I'm going to assume that the cost is Lipschitz. So if I look at the cost for some state S and A, and the cost at some other state S tilde and A, this is going to be less than equal to some Lipschitz constant depending on the cost times the distance between S and S tilde. And I'm also going to assume that my dynamics are Lipschitz. So like when I look at the Wasserstein distance between the distribution starting from state S and A and the distribution, sorry, the same distribution starting from some other state S tilde and A, this Wasserstein distance is less than equal to some constant times the distance between the two states. It can be shown, this is similar to what we did for the span norm. Under these conditions, I know that my value function is Lipschitz. I know that the Lipschitz constant of the optimal value function at time t plus 1 is less than equal to LCT plus LPT times the Lipschitz constant of the value function at time t plus 1. Okay. And from this, I can get a instance independent bound on the Lipschitz constant of my value functions also. We are going to be using Wasserstein metric as our IPM, so the Lipschitz constant matters, but I can also just solve the MDP thing and use the Lipschitz constant of that. Okay. And in this terminology, it should actually be V hat, because hat was my MDP. This is my, I'm assuming my MDP is smooth. Okay. So now, in order to show that this is an AIF, I'll have to quantify epsilon and delta. So let's try to find that out. So let's look at what I have to do is the expected value of the per step cost ST AT conditioned on HT AT. Let's make them realizations. Minus the cost. This is the cost of my model if I take my estimator and get the estimate of the state and AT. Right? I would like to bound this distance. Okay. We know from what we did for POMDPs last time that this guy I can write as summation over all values of state, belief at time t that the state takes that value, Ct of S and A minus Ct of sigma t Ht and A. This is At. Okay. So I can write this as, so this is a constant, this is a belief, so I could add the belief inside since this adds to 1, and I can write this as Bt of S multiplied by Ct of S At minus Ct of sigma t Ht and At. So this guy will, from the Lipschitz assumption, be less than equal to the Lipschitz constant of the cost times the distance between S and sigma t Ht. Okay. Which means I can upper bound this whole thing in terms of LCT and let me call eta t. This is a function of the history where eta t of h t is defined as the expected value of the distance between the state at time t and the compression of the state at history h t conditioned on the history h t. Okay. This seems like a meaningful object. I am asking what is the difference between the true state of the system and my estimated state of the system on average. So, where I am averaging over what the true state of the system is. So, going back to this type of an example, if I choose this as an estimate, I am going to be asking, when I look at the error from this point, what will be the average error compared to choosing this as an estimate. So, this is just computing my estimation error at time t. Okay. So, this means I have done this analysis with absolute values. The reason I have done this analysis with absolute values is because the modeling assumption I was starting with was some kind of smoothness of the model, which is typically a symmetric assumption. So, I am going to be using bounds which depend on the symmetric absolute value version of the bound. So, I still want to keep the history dependence, but I would not do the complete averaging an upper bound and a lower bound. I will use the bounds which said I am going to take the upper bound equal to the negative of the lower bound, right. So, I will get that slightly simpler version of my bounds here, and in that setting what I am getting is that epsilon t of the history is equal to LCT times eta t of the history. Okay. The next step is a bit more interesting. So, for delta, I want to look at the Wasserstein distance between, let us say, mu t and nu t, where mu t is the probability distribution of my estimate at the next time conditioned on history and action, and nu t is the probability distribution. This is the true dynamics of the system. So, this is P t of f hat t plus 1 condition sigma t h t and a t. And this is a difficult thing to compute if I want to get a tight bound, because this is going to depend on the dynamics and in some weird sense on my estimation. So, I am going to upper bound it. I am going to, so remember my distance metric here is Wasserstein. So, let me just write things in terms of Wasserstein. I am going to do triangle inequality and say this will be Wasserstein between this and something else plus Wasserstein between that something else and nu t, and this something else I want to pick as something which I can compare. So, I am going to pick this to be the probability of the true state given history and actions. So, I am going to say what is the difference between the next estimate and the next state given the current history, and what is the distance between the next state and the next estimate. So, this is you see this dynamics and this dynamics. So, this will only depend on the difference between these two objects, because both of these are the true dynamics of the system. Okay. So, the first guy is easy. I am just going to write it. You can There is a derivation, but sort of when you look at the final expression, it kind of makes sense. This is mu hat tilde, sorry. This is just expectation of the distance, or upper bounded by the expectation of the distance between ft plus 1 and s hat t plus 1 conditioned on ht and at. Okay, this should be delta t and at. And this is to do with sort of Wasserstein distance, computing the distance between certain objects, and this guy will end up to be equal to the expected value of eta t plus 1 of ht plus 1 conditioned on ht and at. So this, depending on what happens to my estimation error, is going to say, I'm going to say what's going to be my one-step prediction of the estimation error. Again, I'm not giving the proof of this. The proof is straightforward, but the proof relies on the primal definition of Wasserstein distance, which I have not given. So if you have seen how Wasserstein distance is derived in the primal setting, this is a one-line remark. Now, for the other one, the observation is that if I look at mu tilde t, this is equal to summation over all s, the belief at time t that something is s, times the probability distribution of ft plus 1 given s and a. Okay. This is just law of total probability. And I want to compare this distance with this distance. Now, one property of Wasserstein distance is that it is a convex metric. So we can show that the Wasserstein distance between mu tilde t and mu t is going to be less than equal to summation over s bt of s times the Wasserstein distance between pt of ft plus 1 given s and a and pt of ft plus 1 given sigma t ht and a. And I know from my assumption that this guy is Lipschitz, that Lipschitz constant thing is going to come out, and I'll just be left with averaging over this. So this guy will be equal to expected value. I don't think I get an expected value. This will actually just be equal to LPT times eta t, because the expectation is captured in this belief. So what I get now is that delta t of ht and at is going to be less than equal to expectation of eta t plus 1 of ht plus 1 given ht and at plus lpt of eta t of ht. And for simplicity, my epsilon bound did not depend on the action, so I can pick a delta bound which doesn't depend on the action as well to have a simpler version of this. So I'm just going to work with delta bar t of ht, which is the soup over this side over all actions, just to have a simpler expression. And essentially I'm done, right? So I have quantified what the model distance is, what is the distance between the coughs, and what is the distance between the dynamics. Therefore, from what we did 2 days ago, I know that the mismatch operator applied on v hat star of t plus 1 Keep in mind this is the value function of the MDP, and I am working with the absolute value version. So this is the absolute value of this is going to be less than equal to epsilon t of ht plus delta bar t of ht. The metric is Wasserstein distance, so I get Lipschitz function of v hat star t plus 1. Okay. Note that this is not the norm. I am simply taking the absolute value. This is an object which will depend on both h and a, and I have taken a supremum over a in some form on the right hand side. And therefore, I get that when I use, so not the norm, just the absolute value, when I use the policy pi hat composed with sigma on the original model, and I am looking at its difference from the true value function, I can actually get rid of the absolute value because I know this guy is lower bounded by 0. So I will get this is less than equal to twice summation tau equals to t to capital T, this expression. So the main thing is, this was sort of an example I have in mind. Here is one class of approximation algorithms which people use because this is easy to implement, and I want to quantify how good or bad this is. And this AIS bound type analysis naturally tells me what is the right object to look at. Right? This came out simply by computing what the model distance is, and it also comes in naturally in computing what the dynamic distance is in this calculation. So this is the natural way to compare what should be the approximation error for certainty equivalent schemes, and intuitively it makes sense. This is what is my expected estimation error really. And based on this, I can get an expression where notice that both this object and this object depends on eta. Okay? So if I want to have situations in which certainty equivalence will be good, those are precisely models in which estimation error is small, and these are models in which this thing remains small. Right? I know that the estimation error at the next time is going to be small, but when I look at that one step averaging over that, this should remain small as well. So I can get bounds on these types of things and say what my approximation error is going to be. I'm going to give a couple of examples of that in the remainder of this lecture to show how this can be useful for just using certainty equivalence in certain models, but also how this relates to a learning setup. Okay. Before we go there, any questions? Hey, just a remark before we go forward. This bound is a sample path dependent bound because I'll have to be averaging over what is happening with these HT objects. And if I wanted something which was easier to compute, I could have taken the soup norm also. And I'll get soup over eta t over all histories. That will be a much, much worse bound, but it will be easier to compute. Why is that a worse bound? Think of this object. Okay? If I have a good estimation scheme, I would expect this conditional estimation error to be small with high probability. Right? So think of a situation where most of the time I get good observations. Occasionally I get something which is terribly bad. Okay? So I know my estimation is going to be with high probability is going to be good. But if I take the worst case estimation error, I'll have to worry about these tail events which can be really, really bad. So the soup norm here can be terribly bad, while all we care about actually is the performance along the good trajectory. So for practical things, I can do things like what is the probability of me being in a set where my estimation errors are always small, and work with that. let me give one example which illustrates this. And this sort of, to me, answers a question which I had once as a graduate student when I was taking these courses, is that it seems if you look at a MDP model and a POMDP model and ask what things in the world is an MDP and what is a POMDP, basically everything is a POMDP, right? I never really have perfect state observation, okay? But very often we use the MDP solution rather than the POMDP solution. Why is that happening? So here is a simple model which explains that. Suppose I have some dynamics Ft, and I'm going to assume for sort of simplicity, this lies in some subset of the Euclidean space. Let's just, for the purpose of this lecture, assume this belongs to real, just to keep things fairly simple. If I have some dynamical system, I get some observation of this, and let me assume this observation was state plus noise. Okay. And I'm going to make an assumption that the norm of the noise was less than equal to R. So I have a noise which is small noise. Okay. So I'm measuring the state with respect to some sensor. My sensor is a good sensor, but it's not going to be a perfect sensor. In a situation like this, the POMDP solution suggests I actually should look at my value and try to estimate the state based on the history of all the observations that I have received. Okay. I'm going to instead propose a strategy which is the following. Let, as before, let pi hat star be the MDP policy. So the policy that I'm going to use is simply pi hat star t of yt. I'm going to estimate my state to be just equal to what I observed. This is not a good estimate. I'm going to be off with the true value of the state. If I go to estimation theory, this is a terrible estimate because as time goes on, my estimation error is not going down. But from a practical point of view, I don't have to do anything to run this filter, right? This is just look at the last observation, and I'm going to just estimate my state to be like that. And because of the model that I assumed, I immediately have that eta t of ht is less than equal to R, right? Because the estimate that I'm saying is going to be S plus noise, and I know that the value of noise is less than equal to R. So this will imply, without doing sort of a detailed calculation, that my value function of pi hat star composed with sigma minus v star is going to be less than equal to some terms and everything else proportional to R. Okay? And I can substitute things back in here and compute what all these terms should be. But it's basically saying that if I have small noise, the error is going to be small. If I have large noise, this error is going to be large. So I'm working in a real system where I'm doing some instrumentation, putting in sensors, and these sensors are accurate within, let's say, 1% or 2%, which is often the case. In my system, I can just assume that my sensor measurement is perfect and use a policy like this rather than having to do any type of filtering. Okay? All right. So I want to spend some time now looking at trying to think of a learning problem in terms of a certainty equivalent policy. So the setup is as follows. Just want to. I have an MDP, and this MDP cost and dynamics depends on some parameters. So if I think of like the inventory management problem that we have discussed, these parameters are, for instance, the distribution of the demand. Okay? It could even be the costs and so on, but really let's think of this as either distributions of the demand or in terms of what happens to the type of my dynamics. Okay? So I may not know certain component in my dynamics. Suppose I'm doing something, designing cruise control for a car. I may not know what is the mass of the car because that depends on number of people that are sitting in it, right? I want to look at this and compare it with the type of scheme that we are proposing. So for simplicity, I'll assume that this MDP, the state space is X. Okay? And the way I'm going to model this is that I have dynamics P theta and cost C theta, and I'm going to, these are how the cost and dynamics depend on theta. Okay? And I'm going to assume that X is a metric space and theta is a metric space. So theta belongs to some set capital theta, and there is some d theta metric on that. Now, what happens if I knew the value of theta? If I knew the value of theta, there is an optimal policy pi, let's call that pi hat star, and this optimal policy chooses an action at time x, and this policy will depend on theta, right? So I'm going to think of this optimal policy as a policy of this MDP, and this policy depends on theta. So what I'm going to do now is I'm going to construct an MDP S with state space S, which is equal to X cross theta, right? So this is my model where the state space is this thing plus whatever the parameter here is. The dynamics in this S model is really the dynamics in the X model of the X component of this thing, plus a delta function that theta t plus 1 is equal to theta t. So I'm assuming that the parameters of my model are not changing over time. I just have some dynamics. Okay? So going back to the type of inventory management example that I did while discussing POMDPs, this could be a situation where my demand is high or low. My dynamics depend on, so this would depend on theta also, sorry, but my parameters are not changing. Okay? So I have this decomposition of my overall system, and I want to say that this guy now is a POMDP. Because I have an MDP with state space X and theta. I simply observe the X component of this, and I have to choose an optimal policy. Okay? So the policy that I'm going, so in principle, I have to set this up as a POMDP, and I have to solve that POMDP to find the optimal policy. Okay? And that's going to be a fairly hard problem. What we do a lot in practice is, I'm going to take the certainty equivalent policy here. I'm going to construct an estimator, theta hat t is some estimator that I look at the history of states and actions, and from these I construct an estimate of the parameters of my model. In the inventory management example, I look at the demand distributions and so on, and from that I can do, for example, a Bayesian update to find what this is, and this could be the map estimate corresponding to that posterior, or depending on the specific forms of my distributions, I could be running a fancier estimator to figure out what this thing is. Okay? And one possible strategy is that whenever I have to choose an action as a function of, so this is my history of observations in the POMDP. If I have to choose an action given a trajectory of realizations, what I do is I say I'm going to choose the optimal policy of the true MDP. I'm going to, I know what the state of that MDP is because that is part of my observation, and I'm going to substitute the estimated model here. So I'll estimate the model, and this could be done through various means. I estimate the model and I say what is going to be, my policy is simply use the optimal policy of the estimated model. This is also called certainty equivalence in the adaptive control literature. In reinforcement learning, this is sometimes called a plug-in estimator, but it sort of the general policy makes a lot of sense. I have a POMDP. I don't really want to write down a POMDP problem to solve that. This reduces it to simply a problem of saying, how do I do good estimation? And kind of the intuition is, if I have a model where my estimation can be good, then this policy, eventually my estimation error will go small, and this policy should become better. Okay? I'm going to quantify what is the error of this policy compared to the best that I could have done in my POMDP. Okay? I don't want to compare with the best that I could have done in the true model had I known the parameter theta. Okay? That's a false target from our purposes. There's that performance I can never achieve. Right? I am in a partially observed setting, so the best that I could have done was solve this as a POMDP and get some solution, and I would like to bound the distance between the optimal best learning thing that I could have done here versus this very, very simple strategy that I'm proposing. And it should be clear that this is a special case of the certainty equivalence policies that we considered earlier. So in order to quantify the bound, all I need to do is figure out what this parameter eta is. Rest of it would be some expressions which will go into the type of things that we had derived. Right? So rather than doing things in detail, let me just try to figure out what eta would be. I am going to make some assumptions, and I'm going to basically, I need to impose the assumption that this MDP is Lipschitz, right? Because my results were derived under the assumption that the true MDP is Lipschitz. Now, I have simply assumed that the state of the true world is a metric space. The space of my parameters is a metric space. To argue that this has some continuity properties, I need a metric on the product space. The obvious choice of metric is add these two. So I'm going to suppose that my metric on the S space for some x and theta and x tilde and theta tilde is going to be the distance between x and x tilde and theta and theta tilde. And I'm going to assume that with respect to this metric, my dynamics here are Lipschitz and my costs are Lipschitz. So I'm going to say Ct of x a condition on theta minus Ct of x tilde a on some other model parameter theta is going to be less than equal to LCt times dx between x and x tilde plus d theta between theta and theta tilde. And I'm going to have something similar for the dynamics. Okay? In the interest of time, I'm not writing this down fully, but it's essentially going to be the same statement with x and theta. Okay? Now, once I have this, I know that eta t is going to be the expected value of the, so let's recall what this was. This was the expected value of the distance between the true state, I'll write it down here, true state f t, the estimated state f hat t, condition on h t. Okay. Now, the state consists of two components, the x component and the theta component, and I observe the x component. So, this distance will be distance between the x components and distance between the theta components, and distance between x components will be 0. So, this is really equal to the distance between theta and theta hat t conditioned on h t. And the expression that we had derived last time was something which the right hand side depended on eta of h t. So, essentially I get that my estimation error is going to be proportional to the rate at which my parameter estimates are converging to the true values. So, I get that very, very simply as a corollary of the analysis that we had done. Okay. So, again this shows that like variations of these things are there in the literature quite a lot, and the basic trouble with using this way that I have described the scheme is that if I use certainty equivalent policies, it is not immediately clear that my parameter estimation is going to be asymptotically consistent. So, this object might not go to 0. So, what people typically do is you want to add some noise in here to make sure that this parameter estimation is consistent, and that noise is going to add some additional error at every step. So, this is not kind of a holistic analysis of what is happening in certainty equivalent time schemes in adaptive control. But the main point I want to say is in all these different types of analysis, once you understand what is this basic idea of doing approximations, we can derive bounds for different types of variations relatively easily. Okay. What typically gets done in the literature is that there would be 2 lines of calculation preceding something like this, and that's because one is rederiving all the basic approximation results as well. But if we simply view things correctly, all these results fall out very, very easily. Okay. Questions? So, before concluding this, I also want to point out, yeah, sorry. Okay, all right. Yeah, okay. So, so all this I was arguing that certainty equivalence is a good scheme. There are instances where certainty equivalence is a terrible thing to do. Okay? So, I am going to conclude this with kind of discussing when is certainty equivalence a bad thing to do. Can anyone take a guess? Yes, but I mean if I don't have an underlying MDP model, my POMDP is going to be super complicated. Right. So, typically when I am looking at things, I will assume I have a MDP model, but you are right, if it did not have a state space model, then clearly this does not even make sense. But even when I have state space model, there are instances when doing certainty equivalence is not a good thing to do. And these are things wherever I have an what is often called an active sensing problem. Okay. So, let us say I had a POMDP, I have some state here ft, and I have my agent here, and before taking my action, the agent has the option of spending some cost to actually take the observation of the state. Okay. So this agent either, so like the type of example that we had done last class when I was saying when to observe a Markov chain. So let's take that type of a thing, right? I have to estimate the state of the Markov chain, and I have an option that I can spend some cost to get an estimate of the state, and I want to figure out when should I take a measurement. Okay. What happens if I take a certainty equivalent approach here? Certainty equivalence will say, based on my belief, I'm going to assume I know the state, and now I'll ask the question, what should I do in an MDP when I know the state? So if I know the state, obviously it makes no sense to take an observation. So the optimal certainty equivalent policy here will say never take an observation. Clearly, if depending on the observation cost, this policy cannot be optimal. I can make the observation cost 10 to the power of minus 100, and this will say never take an observation, while clearly at that smaller cost, I should always have taken an observation. Right? So it's not something you can blindly apply to any problem, but it's a good approximation for various types of problems, and it is worth checking whether in a particular setting this makes sense or not. Okay. So I was planning to stop here, but we are running a bit late with the refreshments. So I'm going to continue for some time with the next lecture, and then we'll take a break and come back. So in the last part, I want to provide some kind of a feeling for why these types of results can be good for the learning setup. Okay. So this is going to be more at a high level because we can't really do justice to learning problems in one lecture. But let me first spend some time setting up the background, and so the learning problem can be thought of a generalization of what we did in this last example, but typically things are done in the expected discounted cost setting. So let's take a few minutes to understand what the expected discount setting is, and then we'll see what does learning there mean. So first thing that I'm going to assume is that my model is such that P and C are time homogeneous. So that means that these are not changing over time, and I really want to look at settings where my time is going to infinity. If time is going to infinity, that creates some technical problems. If I blindly look at the problem, along every trajectory, the total cost is going to go to infinity. So I have to regularize things in some form so that things don't go to infinity. One of the simplest way to do that is to assume that there is a discount factor. And this is a number between 0 and 1. So what that means is that if I give you any policy pi, and I want to see what is the performance of this policy starting from state time 1, this will be given by expectation under pi summation t equals 1 to infinity, because I have an infinite horizon problem, cost of ft and at, but I'm going to be discounting the future by gamma to the t minus 1. Okay. This ensures that my total cost does not blow up. And similarly, we are going to define v star 1 of s to be the minimization over v pi over all policies. Now, what interesting thing happens if I make this assumption. Because you see, the usual setting that we had was that V, let's write it in terms of pi, V pi 1 was equal to T pi applied to the environment operator applied to V pi 2. Okay. Note here that the environment operator is time homogeneous as well, so I am not writing ET. Now, what is happening is from this point onwards, V pi 1 is the cost to go if I start at time 1, and V pi 2 will be the cost to go if I start from time 2, but that looks exactly the same as the cost to go if I start from time 1. Okay. So, I expect that under mild conditions, these objects should not really depend on time. So, my iterative equation actually reduces to a fixed point equation that is V pi is equal to T pi E of V pi, and by a same argument, the optimality equation will reduce to something like this. I am looking at an infinite sum. I need to worry about things not blowing up. Okay. Yes. Okay. But like formally, right, if I want to show this is optimal, I would have to argue this is just a made up problem. I'll have to argue this as a solution, and then I'll have to argue from first principles that this solution is going to be an optimal solution for the original infinite horizon problem. Okay. So, I'm sort of ignoring all that, but if you look at a standard book on MDPs, there would be about 3 or 4 results that I need to establish in order to say that the policy that I get from this is optimal. Right now, I'm just trying to provide an intuition on why there should exist a solution. Okay. Now, equations of this type are called fixed point equations. And it can be tricky to establish that such a fixed point equation has a solution. Okay. So, we want to say there is a solution on the right hand side that when I substitute it here, I get back the same thing. Now, one thing which allows us to show that this thing has a solution is, recall that in the finite horizon case, I had shown that if I look at this thing, this was a non-expansion. Right? Now, what's going to happen here is I'm discounting the future by some discount factor. So, that same proof shows that this is actually a contraction. Okay. The discount factor will show up in my norm, and recall that both of these guys were non-expansions. Okay. So, if this is a contraction, the composition of these two is a contraction. So, I get that these are fixed points. I am looking for fixed points of a contractive operator. There is sort of this result which is known as the Banach fixed point theorem, which says that in a metric space, if I have an operator which is a contraction, it has a unique fixed point. So, we are going to take the metric space of the space of value functions and the metric to be the sup norm, and I know in this space I have a contraction. Therefore, this will imply that both these equations V pi and V star are unique bounded solutions of let's call these equations A and B. It can also be shown that if I look at the policy which achieves the optimization here, that policy is optimal. So, the good thing is I will get a single policy here, pi star, which is the greedy policy with respect to V star, and we know that just using the same pi star all the time, this time homogeneous policy is optimal. So, the reason why people like to work with infinite horizon problems, although in reality I am never working with an infinite horizon problem, nothing is going to last forever, but that modeling assumption makes the implementation really, really simple. I have to work a bit harder to find these fixed points. I am not going to talk about algorithms to compute these fixed points, but there are a huge number of algorithms which try to compute these fixed points efficiently. But the key advantage is that I can implement this optimal policy in a relatively simple manner, because I am only implementing one policy rather than a time varying policy. Okay. All right. Now, what do we do in learning? So, in the learning setting, one would imagine a case when P and C are not known. And I am interested in an algorithm which tries to estimate P and C, or estimate them in some form, and then argue whether I am going to converge or not. So, one of the questions which is asked in this case is the question of sample complexity. So, the sample complexity question is the following. I take some learning algorithm, right? Let us say the certainty equivalent algorithm that I had prescribed earlier. I could imagine that certainty equivalent algorithm is equally valid for the infinite horizon problem also. And rather than quantifying the error over time, I ask the reverse question. I say that I want to run my learning algorithm for sufficiently long period of time such that my estimation error is less than 10 to the minus 3. How long should I run my algorithm? Okay. And for different types of algorithms, people can do analysis of the runtime of these algorithms. But I can also ask, what is the fastest any algorithm could learn? And one way to characterize that is looking at the simplest scheme, which is known as working with a generative model. The idea here is as follows. Suppose I don't have a mathematical model for the real world, but I have a system simulator which is perfect. Okay. So, maybe I have this 12 joint robot, and I have a simulator which does all the underlying physics, and I can figure out that if I give this an input of a state and an action, what the next state would be. Okay. So, the question I can ask is the following. Let me use this generative model to learn a model, use certainty equivalence on that model, and try to estimate how many samples do I need in order to get a good estimate. And that has to be some kind of a lower bound for any learning algorithm, because any other learning algorithm will actually have to act in the real world. So, if in this simple case where I could just input whatever I want and get whatever I want, if I cannot learn fast enough in this, any algorithm will not be able to learn faster than that. Okay. So, how many samples do I need in this generative model setting in order to find a good policy? So, the simplest way to do learning in this setup is as follows. I look at every state action pair. So, I look at every state action in S cross A. I pick a number n, and I am going to give n inputs with S and A. Okay. This gives me n outputs for the next state. And I am going to generate a estimate P hat n of S prime given S A to be equal to, I am going to count how often when I gave S A the output S prime came divided by n. Okay. This is the simplest form to construct an approximate model. And I would like to figure out how good or bad this model is. Now, before doing that, I actually forgot. Before we get here, we have to look at what happens to our approximation bound results for the discounted setup. So let me go back and say what will happen to the discounted cost results, and then we are going to come back and continue this problem. I'm going to describe what happens to the bounds for the simplest setting, which was the true model and the approximate model were identical, and I'm getting bounds in terms of the soup norm. Recall those were our simplest bounds. The other bounds are also going to extend in the same way, but once you understand what happens in that case, everything else is sort of conceptually the same, the details differ. Right? So my setup was, recall, M is S, A, and now I'll say P, C, and gamma, and I have an approximate model which is S, A, P hat, C hat, and gamma. Okay. And my mismatch functional, again, this will not depend on time. This is E of V minus E hat of V. Which becomes equal to C plus gamma PV minus C hat minus gamma P hat V. Okay. So I want to understand what happens to my error in terms of this. And recall that the type of bounds that we had were saying that my error, let's just think of this object because other bounds were similar in nature. Recall that we had said that this is going to be, if I was looking at time t, this was less than equal to summation tau equals to t to capital T norm of d v pi t, or this was also less than equal to norm of d hat d of v hat pi t, t plus 1, sorry. Okay. And we were taking the minimum of 2 and picking whichever bound was appropriate. Now, what happens in the infinite horizon case? Essentially, I have the same result. This will not depend on time, and this will not depend on time. This will go to infinity, right? So the expression, and notice that there is this discounting which is happening here. That discounting will really mean that I need to do a gamma of t minus tau here. So when I was looking at the future was being discounted by gamma, that discount factor will come up here. Okay. And by sort of the same argument, these things should not depend on t. So roughly what I expect in this case, when I go to the infinite horizon setting, if I just take the finite horizon result and extend that, I should get things which is now, this is one object and the sum of a geometric series. So this should be 1 upon 1 minus gamma times d of v pi, or less than equal to 1 upon 1 minus gamma d of v hat pi. Okay. Does this make sense? So when I do approximation bounds for infinite horizon, I should get much nicer looking expressions, because I'll start getting things which are like geometric series. Okay. The model approximation bound, when I'm looking at a true model and an abstract model, that remains similar. The sample bias bounds are a bit more difficult because we'll have to either argue things become time invariant or do certain things. But let's just focus on the soup norm just in the interest of time rather than anything else, that I'll have this clean results here. Okay. Now, notice that in the soup norm bound case, I was emphasizing this part. I was saying I have one result which says V minus V star soup norm. Translated to this thing was, one result was in terms of the mismatch operator of V hat star upon 1 upon 1 minus gamma, okay, or 2 upon 1 minus gamma. There was another result which I was saying is useful in the learning setting, where I want to get everything in terms of dV star, right? And that had some additional time terms. In that setting, again, without going into too many details, we can show that that other result is of this form. Okay. Remember, that was sum of future costs, and then so this result was of the type t minus tau plus 1 d of dv star t plus 1 tau equals to t to capital T. Right. So it has two summation over time type of terms. And this one gives upon 1 upon 1 minus gamma, and this gives 1 upon 1 minus gamma. Sorry, this other summation gives 1 upon 1 minus gamma. Therefore, I get 1 upon 1 minus gamma squared. Okay. So we'll take that this is the result that we get, and using this, I'll come back to this sample complexity question and try to see what I can say in this setting. So, and for simplicity, I'm going to assume that my cost is known. So I only have to learn the model. The cost function was known, just to give the flavor of the type of analysis that we have to do here. So notice that my error bound, I'm going to use this error bound, and the error bound will depend on dV star. So let me just write dV star. dV star is going to be E V star minus E hat V star, and this is going to be C plus gamma P V star minus C plus gamma P hat N V star. Okay. So this object is equal to gamma times P V star minus P hat N V star. Let me write out this square term in full. This is summation P of f prime given S and A V star of S prime minus, so I'm going to write this for a particular f and A, minus summation n equals to 1 to capital N, 1 by n V star of Sn prime. You see, if I go back to my sampling process, this was number of times I got f prime n. So I'm going to say, when I look at my number of samples, how often did I get this divided by n? This object is equal to p hat n. Yes, so this is sort of conditioned on the same f and a, right? This was my sampling process for my generating model for a given f and a. So sort of my notation should carry f and a here also, but I'm trying to give the complete main idea without having all the details here. So this starts looking like a concentration inequality. Right? Fix f and a, I have a distribution on the next state. The first object is the expected value according to that distribution. The second object is I get n independent samples, and I'm saying how is the sample mean close to the expected value. So I can take my favorite concentration inequality and I can try to bound that. Right? So concentration inequality will say probability this entire thing is greater than or equal to some alpha is going to be less than equal to something like 2 to the power of minus some rate which depends on the model times alpha, right? I'll get this type of results. So in particular, for something like this, I can use Azuma inequality to quantify what this guy is going to be exactly. Okay. So I could go and write that, and let me write the Azuma inequality. Azuma inequality will say this greater than equal to this is less than equal to twice exponent of minus 2n. Let me call that C because alpha was the specific thing in my analysis. So 2nc divided by h squared, where h is equal to the span of V star. Okay. So I can look at some concentration inequality, say Azuma's inequality, and that's going to say that the probability this guy is greater than something is less than equal to this. So from Azuma, I can also now get, by using union bound, probability that the norm of this object is greater than equal to C. So norm of this object greater than equal to C means that this guy should be greater than equal to C for, Azuma would say this is, I'll use it the other way around if I want to use the bad events happen, right? Okay, yeah, this is fine. So I want this to be greater than equal to C. I'll say each one of these is greater than equal to C. That's what the union bound will say. So this will be less than equal to twice cardinality of F times cardinality of A times exponential of minus 2 nc upon h square. Yes, you see, but what I want to do is any one of them becomes greater is a correlated event. So I'm just going to use union bound that, right? So and that will give me the number of objects that I have. Okay. So yeah. Yes. So this is there, right? So this is really you have concentration inequalities for total variation. This effectively is a total variation concentration inequality, but we also have concentration inequalities for Wasserstein distance and so on. Those tend to be a bit more messy than something like this. Azuma is very, very clean, but those can be much tighter than Azuma. So we can't pick IPM distance type thing. But notice that there is no IPM distance, right, in what I'm talking about. I'm doing analysis here, right? Yeah, but now the object that I want is the norm of dV star, right? If I upper bounded this by epsilon plus gamma IPM distance times V star, that bound is much, much looser. Azuma is much tighter than, so you see, I could have taken this guy and upper bounded this by delta of P hat times rho of V star. This will give me much poorer concentration. I mean, there's a reason concentration inequalities talk about concentration of expected value rather than concentration of measure, because concentration of expected value is much, much faster than the concentration of measure. So basically, we are done here. I can set this guy equal to whatever object alpha I want, and I can invert this to figure out a value of C. So effectively, which will say that if I want this thing to be equal to, sorry, not alpha here, I want this thing to be equal to alpha. Probability of, yeah, sorry. So what would I want is this quantity to be equal to delta, this quantity to be equal to alpha. And once I get that, I will get that width. So I invert this to figure out n in terms of this guy and this guy. And I'll get with probability 1 minus delta, my error is at least something. Okay, it will not be alpha, it will have to be the scaled version of alpha, but I want this object. This is the bound that I have, right? So I want 2 upon 1 minus gamma squared of this guy to be less than equal to something to be less than this. And I can solve all of this for getting a value of n, and I get that the number of samples that I need in a generative model to get an estimate which is within alpha of the true thing with probability 1 minus delta must at least be this. This is one of the simplest way to derive this sample complexity bound for generative models. These results are not the tightest. Essentially, to get tighter results, one needs to do some version of Bernstein inequality rather than Azuma here, but doing it in this form does not work. There's a slightly more detailed analysis that gives a tighter bound than this. But even with this very, very crude bound, one recovers the sample complexity bound in the simpler case. Okay? So this kind of shows that this question of model approximation comes up quite a lot in the learning setup, and it's useful to have these results in the back of your mind because it simplifies, for instance, the derivation of this part. I can really directly pick the existing results and say, this is the object that I want to analyze, and now you'll have to use some model-specific things to do that analysis. Okay? So I have one more thing to talk about. So maybe I can just continue for a few more minutes and finish that, and then we break. So the last example that I have is something where this type of model approximation bound shows up in a very, very unexpected way, or at least it was completely unexpected to us that this bound will show up there. So let me motivate a bit in terms of what the setup is. So one of the popular algorithms in the learning setting is Q-learning. Intuition behind Q-learning is the following. So first of all, in a learning setting, I have two options. I can either try to learn the value function, or I can try to learn the Q function. If I try to learn the value function, I will separately have to figure out the policy in some way. So people prefer to learn the Q function, because if you have the Q function, I have the policy from the minimization of the Q function. So if I have any algorithm which asymptotically converges to the optimal Q function, sort of I am done. Now recall our recursion for Q function. The fixed point for Q function is Q of S and A is C of S and A plus gamma times summation S, this is Q star, S prime, P of S prime given S and A, V star of S prime. Okay. Now, I am going to write the entire recursion in Q, so I am going to write this as this minimization, just so that I can get a fixed point recursion which starts from Q and gives me Q. And just as we argued for value iteration, for value function, this thing is a contraction, this operator is also going to be a contraction. Right? I'm really writing E followed by T star rather than T star followed by E. So this is non-expensive, this is contractive, therefore this guy is contractive, and this thing will have a unique fixed point. Now, one of the implications of Banach fixed point theorem is that I can do the following recursion. I can start with some guess q0, and I can start computing q k plus 1 to be equal to this operator applied on qk. Okay. And this iteration will converge to q star. So, we can show that this thing will converge to q star. This is one of the corollaries of Banach fixed point theorem. Now, in the learning setting, I can do this object, I cannot do this thing. Okay. So, let me consider the following setting. I am going to take a policy which gives from state, this could be randomized, so state to distribution of actions, which is called a behavioral policy. So, a behavioral policy is a policy where I decide to act in the world according to some policy. This thing is going to give me a sequence of state and actions, and I get the reward cost at this time, and then the next state, next action, the cost at next time, and so on. Okay. In the RL terminology, this is called an experience. So, what I am going to do is, I want to run this algorithm. I want to learn the finding the fixed point using this, but I don't know how to take expectations. I am getting this object, I am getting a sample from this, and I am also getting a sample from this. So, Q-learning says, naively, I could try to do the following. This thing does not work, but let me write it down so that we can explain what happens. So, I am going to say if at time k I had experienced sk and ak, let me do this to be equal to ck plus gamma times, let us write this as vk of sk plus 1. Suppose I do this, okay. This guy is an unbiased estimate of this guy. If I take the expectation over all values of sk plus 1, I will get this thing. This is a terrible thing to run, because I am just looking at noise, right. So, if I want this to converge, we have to do what people do in stochastic approximation. So, rather than this, what I should do is I should say with probability sum 1 minus alpha k, I keep the old value that I had, and with probability alpha k, I am going to take this new value. Okay. And stochastic approximation theory says that since this guy is a contraction, so stochastic approximation theory primarily says that if these learning rates alphas are chosen in such a way, then this discrete iteration is going to track the trajectory of a continuous time ODE. If this calculation that I am doing is a contraction, then that continuous time ODE is going to be globally asymptotically stable, and therefore, this iteration is going to converge to the optimal Q function. So, that is kind of the basic idea of Q-learning, that if I start with the behavioral policy, there are few assumptions here. This behavioral policy should visit every state action infinitely often. These learning rates have to satisfy some conditions. Under those conditions, I can use stochastic approximation theory and argue Qk converges to Q star. We were interested in understanding what happens to this type of learning algorithms for POMDPs. Okay. So, the simplest setting for POMDPs, and this is what people do in experiments, is I cannot work with a belief state, so I have to come up with an approximate information state. The simplest approximate information state is that I just take my information state to be previous few observations. Okay. So, I have this sliding window and I look what I had observed in the previous time steps and I use that. I run this type of Q-learning algorithm, I plot training curves and I see what happens. Okay. And the question is, does this type of Q-learning algorithm, will that converge or not? I'm going to sort of explain what happens in a more general setting if we had just some fixed update function of the type that we had been talking about earlier in the course. So, suppose I have a AIF which is recursively updatable. Now, the issue is that something like this is not going to be an MDP. But what people do in practice is they say, I'm going to still run the following algorithm. I'm going to take some behavioral policy and I'm going to say this is with 1 minus alpha k. I'm going to take qk, the old qk, and with probability alpha k, I'll do the update pretending everything is Markov. Okay. And there are a lot of empirical results which suggest that doing a calculation like this converges. So, if one tries to, I cannot really do the type of analysis that is done in standard Q-learning analysis to say this converges, because it does not have the Markov property for Zk. Zk is not a Markov process. Nonetheless, one can do the following. So, for analyzing these types of problems, one interesting observation is that Sk and Zk is a Markov process. Okay, because your environment state is evolving in a Markovian manner, and if I know how environment state, if I have access to the environment state, I can get a distribution of Yk plus 1, and therefore, this whole thing will become Markovian. Okay. So, in this setting, what one can show is that if my behavioral policy had certain properties, then this Markov chain is going to converge to a stationary distribution. So, let zeta, which will depend on my behavioral policy, be the stationary distribution for the above Markov chain. Then, using stochastic approximation, one can show the following, which is that qk here converges to some q hat star, where q hat star is the solution to the following MDP. I have a C hat mu of SA, which is summation over S So, from the stationary distribution of my Markov chain, I can compute this marginal distribution, and from this thing I can also compute So roughly what this is saying is the following. If I look at a Markov chain and ask how frequently do I see the cost S along my trajectory whenever I was seeing Z and A, that is going to converge according to this distribution of the Markov chain. Okay. Therefore, I can say that on average in, sorry, this is state Z, these are Z dynamics. On average in state Z, I am observing a particular cost according to this probability. Right? This is how I will get from Markov chain analysis. And on average, the number of time I am seeing Z prime when I was in state Z and A are going to depend on how frequently do I see Y when I am in Z and A, and that will depend on something like this. So it's not sort of, if you know stochastic approximation, it's not too hard to see why I expect my this dynamics to converge to the fixed point of this, because on average this stochastic dynamics, this Q-learning algorithm is seeing cost and dynamics which are like this. But the interesting question is, this thing converges, but can I argue how good or bad is the policy that I learn from this compared to my true policy, the best that I could have done using the entire history. Okay. And since I am converging to the solution of an MDP, I can just pose this as an AIS approximation bound. Right? I know, let me pretend this is an approximate model to the true model. I have some feature already which gives me Z as a function of history by unrolling this type of dynamics. I know this thing is, these dynamics are mu P hat and C hat. I can try to compute the model distance between this and the true dynamics, and that will tell me how good or bad my convergent solution is. Okay. So, this was not immediately obvious that if we are analyzing some algorithm of this type, we are going to get approximation bound, which will depend on the AIS style error analysis. But it turns out that this is also important in analyzing learning algorithms. Okay. So this is sort of the different type of examples that I wanted to present, in which we can directly use the results from these bounds. So there are a lot of details here which I did not present, but the high level thing is, at the heart of a lot of these learning questions, the analysis of learning algorithms is this question of what is, I'm learning something which is going to be optimal with respect to some model, and if I want to see how good or bad I am learning, I can just say what is the distance between the model that I learn and the true model, and use the model approximation bounds to characterize performance of learning algorithms. Okay. Any questions on this? All right. If not, then I'm done with all the material, and thanks everyone. Yeah.